Oh, hi there. Thank you for showing up for your learning. It's Grant, the SAT Genie, and we're going to walk through Practice Test 3, Section 4. Practice Test 3, also Section 3 in this video. Have I ever mentioned that numbers do this weird, swim around on me thing if I'm trying to talk and do math at the same time? You may notice it today as I talk about these math questions. So let's get started with a 1 minute mindfulness, which is 3 breaths. My first breath is about my body. I just observe, notice that my back is a little tight, and that I might like it if I had a heated blanket. But I'm not going to get one. So I'm too excited to do math. My second breath will be about my mind, just a chance to observe. Just like goes from like 15 voices to no voices. It's very busy in the mind until you start to look at it. And then it's like flipping the lights on and all the roaches scatter. That's sometimes how I feel when I do this, just like so clear after I take the second breath. Third breath, I'm going to visualize SAT success for you all, particularly on these types of math problems. That was pretty cool. One of you is doing so well in your SAT math, in my imagination, that you not only did you score a 780 on the math section, but you thought I was going to go through for journalism. But now that I scored so well on the math section, I'm thinking I'm going to do something connected to journalism and math. And you kind of created yourself a new niche and a new type of career for yourself. So I thought that was pretty cool. All right, so now let's get started. We're going to take a look at question number 1. So if I have a wall of text type question like this, I'm really going to highlight some things. So I have n walls. So n is the number of walls. So I'm just going to mark that up as I go. With the same size and shape with a specific brand of paint. The painter's fee can be calculated by the expression. So an expression is like a type of equation that would denote how much they pay. NKLH, where n is the number of walls, k is a constant with units of dollars per square foot, L is the length, and H is the height. Okay, so if I have like walls where H is the height and L is the length, and I have n of them, and then I multiply that by this constant k, this is how much money you're going to have to pay this painter, or what the painter will charge. If the customer asks the painter to use a more expensive brand of paint, which of the factors in the expression would change? Okay, so first, if it just like immediately jumps out at you that it's K, then you circle K and move on, because that's correct. And it makes perfect sense with the way these types of expressions are built. But that's of limited value to you if you're struggling. So let me help you if you're struggling. Eliminating variables would be very useful. If we're using more expensive paint, it's not going to increase the number of walls that we're doing. It's not going to increase the length of the walls or the height of the walls. The only thing left is K. Circle it. So this is a good one for elimination. You can eliminate all the other possibilities, or you can just read it and know that the constant would be related to how much the painter is charging for this type of work. So more expensive paint, he's going to charge more, or she or they are going to charge more per wall, per number of walls. Okay. These ones here, a to the 2/3. It's the same as one of these expressions for all values of a. Okay. We will practice these skills, and you will see them, especially when we look at exponentials in our third week together. But essentially, here is the identity. If I have x raised to the power a over b, then that's equal to the b root of x raised to the power a And that's the annoying way to do it, but it's often the way that the SAT will write it. And it's also equivalent to the b root of x all to the power a. I like this one better, but this one here, you'll notice that the numbers swam into just the right spot there. So this one, if you just know the identity, that this is called a rational exponent, and this is the radical form. You want to be very good at going between the radical and the rational form, and that makes this question a 10-seconder, a 20-seconder. Like you just look through, oh, there it is right there. Okay, so let's look at it. We have a to the 2 over 3 is equal to the third root of a squared. So this number will become the exponent. This number becomes what we call the radicand. The index number of the radical. Okay. All right. So that was question number 3. Question number 2 is here. I'll do them in order next time. Okay, we have an equation here. 3r is equal to 18. What's the value of 6r plus 3? There's a lot of ways to do this one, but probably you did it this way. You probably said, well, if 3 multiplied by some number is 18, then I'm allowed to divide both sides of the equation by the same thing to get r is equal to 6. Cool. And if r is equal to 6, I can just substitute that. I want to know the value of 6r plus 3. Do not choose that one. We are not asked r equals what. No, we're not. We're asked what's 6r plus 3. So 6r plus 3 is going to be equal to, I take 6, I substitute 6 in there for r, and I always substitute into brackets, then I add 3. Okay, so that's the same thing as 36 plus 3. That's 39. I go and I look for it in the answers. There it is. Okay, maybe, yeah. So there's a faster way. The faster way looks like this. I'll just show you. If I know 3r equals 18, and I've been asked to find the value of 6r plus 3, I can write 6r plus 3 as 2 times 3r plus 3. See, this is 6r, right? 2 times 3r. It's the same thing as 6r, but I already know what 3r is. So I know that this is 2 times 18 plus 3. 2 times 18 happens to be 36 plus 3, and then we get 39. So this one can become a 10-seconder. You can do that in your head and then check it and be very confident. Okay, let's keep going. Now we get to question number 4. All right, the number of states that joined the United States between 1776 and 1849 is twice the number of states that joined between 1850 and 1900. If 30 states joined between these two dates and X states joined between this and this, then which of the following equations is true? There's a few ways, again, to approach this one. And I'll show you maybe the most natural way, and then I'll show you if you want to find a shortcut. Okay, so first of all, zoomed in a little much, aren't we? There we go. So here's something that we know. We can go ahead, we can even calculate X, okay? This number is twice the number that joined in there. So we know that 30 is equal to twice the number that joined between 1850 and 1900. So in other words, here, divide both sides by 2. 15 equals X. So if I know 15 equals X, I can just go ahead and find the one that works. It's certainly not that. 30 times 15 is not 2. Oh, it's that one. Notice I didn't even need to solve it. And that's what I was going to show you, is there's a shortcut available. That's the linear equation that we create from this situation. Looks like that. So that's the correct answer. Okay. 15 divided by 2 is certainly not 30. And 15 plus 30 is certainly not 2. So those we can eliminate if we figure out how many states joined the Union between 1850 and 1900. And yeah, I would just, they're looking for, can you create that expression based on this text? The others are all incorrectly formulated using 30 and 2. So formulate your expression correctly based on the text. You read it, you understand it, and then you create an expression. If 5 over x is equal to 15 over x plus 20, what's the value of x over 5? Okay. So with this one, you could say that there's a shortcut available, but I don't really love it. Okay, I'll show you what I would do. I would just do this the straightforward way. So let's start in blue, my favorite color. And we're going to go 5 over x is equal to 15 over x plus 20. And then in this case, we can multiply both sides. You can multiply both sides by x. So you could do this. I don't kind of like showing it this way. Okay, so I'm going to multiply both sides by x. And I'm going to multiply both sides by x plus 20. Okay. So I multiply by both factors. On this side, the x plus 20 cancels that one. On this side, the x cancels that one. And I end up with, on this side, 5x plus 100 equals 15x. Subtract 5x from both sides, and we get 100 equals 10x. 10 equals x, and we were asked for x over 5. So that would be 10 over 5 equals 2. This is the value of x over 5. There it is. Notice that they will often try to catch you with that trick and say, hey, how about you did all this work to find x equals 10. Why don't you pick that, right? And we're not going to pick that. We're not going to fall for their tricks. All right. Here's another way of approaching this. I think I lost some of you when I multiplied by two factors. That was designed to knock out the fractions on both sides and give me a really tidy expression to work on. But I can actually get there with one of my preferred algebraic shortcuts, and I'll just copy this expression again in black down there, and then we'll scroll down and do it. Okay. So if I have 5 over x equals 15 over x plus 20. What do I do with that? Let's see. This is going to be x over 5 equals x plus 20 over 15. Flip both sides is an acceptable inverse operation in algebra. I don't like that my variables are on the bottom, so I flip both sides, and then I boldly multiply both sides by 15. Giving me 3x, because this 15 divided by 5 is just 3. And these just cancel. 3x equals x plus 20. And then you'll see that 10 is still the solution to this. We subtract x from both sides. Get 2x equals 20. X equals 10. Come on. Same. But we don't proudly give that as the answer. Please get those points. Please know that they did not ask for the value of x. They asked for the value of x over 5. And we give them what they want because we want their points. Let's keep going. Ooh, a system of equations. So if you're doing one of these a day, this is a very fast question, and you are pleased to see it on the SAT. You hope to see many of them on the SAT because you're going to be real good at them. Notice that they didn't ask you for X or Y. They ask you to, again, do something with both values. So here's how I would do this. I would just go ahead and copy it out somewhere. 2x minus 3y. No, you wouldn't, Grant. You would do it in your head. Yes, I know I would do this in my head. But I can't show you that then, can I? Equals minus 6. I also can't do it in my head and talk at the same time. That's another thing I can't do. Someone out there can do that. Probably lots of people, but I can't. So I'm first going to multiply the equations by something to create an opposite coefficient in one of my variables. So I'm first going to eliminate the x's, and then I'm going to and I'm going to do that by multiplying the top equation by 3 and the bottom of equation by minus 2. So that top equation, I'm going to write it down there after I multiply everything by 3. 3 times 2x is 6x. 3 times negative 3y is negative 9y. And then 3 times negative 14 is negative, he says 42. There we go. Got it. Yeah. All right. And then I'm going to multiply the bottom equation by minus 2 and put that down there. Okay, negative 2 times 3x is negative 6x. If you know me, you know I always do this, and I always create a coefficient that can add together and eliminate, never subtract and eliminate. I don't like it. I always add. Okay, negative 2 times negative 2y gives me positive 4y. And don't forget to multiply your constant. Negative 2 times negative 6 is positive 12. Okay, now we add these together, all of the different terms. So 6x minus 6x is 0. Negative 9y plus 4y is minus 5y. And negative 42 plus 12 is negative 30. And then we divide both sides by negative 5. We don't need to worry about this 0 because it's 0. It's not there. And then we divide this by negative 5 to give us y is equal to 6. And why don't they give that as one of their answers to fool some of our colleagues? I don't know. Now, you got two options for how you go ahead and find x. In this case, I would just take the easier to work with equation. They're both easy to work with. And then I would just go ahead and substitute in. Okay, so I'm going to say this one is marginally easier to work with. I don't know, super easy. Okay, 3x minus 2y equals negative 6. And then I go ahead and substitute that y in right there. Okay, 3x minus 2 multiplied by 6 is equal to negative 6. All right, cool. Let's add 12 to both sides of these equations. Okay, because negative 2 times 6 is negative 12. If I add 12, I got a 0. 0 is really easy. So I got 3x plus 0 equals negative 6 plus 12. That would be 6. And then we divide both sides by 3. And then we get x equals 2. Okay, so if y is 6 and x is 2, and we've been asked, to find one of these values. Oh, right, it was up there, x minus y. So x minus y equals 2 minus 6. You can substitute into brackets here if you want to avoid making errors. And 2 minus 6 is negative 4. There it is. Here's your answer. All right, let's keep going. Okay, that's 6. I'm going to do 7 next. All right, let's go. Okay, yeah, so we've got a polynomial here, and we've been given a table of values. And this one is testing, do you know a special property about polynomials and their factors, particularly related to the zeros of a polynomial, okay? Where does the function have an output of 0? Okay, I'm going to draw a function for you, and you're going to be able to see it, okay? If I have a function like this, gross, okay? My quick sketch of a parabola, okay? And I know that these are the zeros. Those are where the function has a y value of 0, okay? And if you recall from quadratics, if those are factors, like let's say this is at the point 1 and this is at negative 2, okay, this is 1, all right, then we might have a quadratic that looks something like this. X plus 2 multiplied by x minus 1. It's worth it now actually to pop over to Desmos, and I'll show you this in Desmos. Okay. Oh my gosh, don't look at that. I forgot I was going to need Desmos here. Open to my email. It's embarrassing. All right. So here, let's look at them. If I have x plus 2 multiplied by x minus 1, look at that, just like I said, it would have zeros at the flippy values, and I say flippy values because that's minus 1, and this is over here plus 1, and this is plus 2, and that's over there at minus 2, okay? And even if I have like some number multiplying that, and that number is changing, doesn't matter how I change that number, it will always have those zeros. But what if it's a polynomial with multiple x's? Well, if it can be factored, it would be of like this form, x minus 6, let's say. And then we're going to make this a quartic, and we're going to go x plus 3. All right, let's make a really small so we can see more of it. Oh, even if it goes like 0.1, it's still big. There, okay. So you see here, it still maintains those zeros, okay? And this is a property of polynomials. one of the reasons, sorry, that it's doing this is if I input a value for x that makes one of these factors 0, then it will have an output of 0. Okay, so if I input 1 for x, it doesn't matter what that a value is, I'm going to have a 0. Okay, if I input 6 for x, 6 minus 6 is 0. So that's going to output 0, because anything, doesn't matter what these other ones are. 6 plus 3, 9. 6 minus 1, 5. Okay, so those multiply together make 45. That's already a big number. 6 plus 2, 8. 45 times 8 is rather large. Oh my goodness, what's wrong with my brain? It's 340, right? 340, wow, it's so big. But no, it's still 0 because it's being multiplied by 0 there. That's why it's coming from like such a high height and just diving down there, because it's like it was really big, but as soon as one of them is approaching 0 or hits 0, phew, comes down. That is all to say that in this case, you see, we notice this on the table and we're like, okay, zeros are significant, particularly when we've got polynomials. We want to know there are some factors of f of x. Like this function, f of x, could be written as x minus a times x minus b dot 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 other factors. We don't know what degree the polynomial is, but we know that if you have x equals 4, and then f at 4 would equal 0, okay? And if you know that, then you know x minus 4 is one of your factors. This one. That's all. That's very fast if you really got your definitions. So if you have any questions about this stuff, like I'm not really trying to teach this from the ground up here. And in this case, I kind of did a brief explanation that's a little closer to the ground up. But if you want more and you have questions about this, you send me a quick email and then we'll have a chat at our next class, or I'll send you a custom video based on your misunderstandings. Okay, here we go. We have a line and it's kx plus 4. Cool. K is a constant. Sure. And it's graphed in the xy plane. If it contains the point CD, where C is not 0 and D is not 0, what's the slope of the line in terms of CD? Okay, that's pretty cool. All right. It helps to visualize. Okay, so normally we have y equals mx plus b. And b gives us the y-intercept, also known as the initial value. And m is the slope or rate of change. We don't know this slope. It's unknown to us at the moment, but we do know that the line goes through the point C and D, so we should be able to express the slope in terms of C and D. So we want to start with a visualization. Here is my xy plane. I'm going to take an arbitrary point out here and label it CD. If it's not there, it doesn't matter. I can move that around. I'm just going to use the x value as C and the y value is D, okay? And then over here is this line's y-intercept, which happens when x is 0 and y is 4. Okay, well, how do I know that? Because 4 is the y-intercept, okay? And now I go ahead and get another color because I want to do a beautiful diagram. You're not going to need beautiful diagrams on the SAT, but you do diagram this out so that you know you're going to get all the points. And then I put my line through it like that. Okay, it's going to be some line like that. And the slope of that line is determined by K. But the slope of that line is also, as you can tell, totally determined by that point CD. Like if CD were down here, K would be negative. But it's not. I arbitrarily put it up there. In any case, when I draw my rise and run triangle from here, this is going to give me my change in y and my change in x. And m, which in this case is k, okay? K is, they put k there, all right? M there. M is equal to change in y divided by change in x. But we know that x started at 0 and went out to c. So the change in x is just c. So we can eliminate this one and eliminate that one. They're not it. The change in y, we can say it starts at 4 and ends at d. So it rises d minus 4. So that would be this one. Now, how do you know it's not 4 minus d? That's actually a pretty good question, all right? Because here, down here, c is positive. So another way of writing this formula, and this will help because I often don't use this formula. I often just use visual, but I'm sensing that many of you use this formula. So let's take a look at it. Change in y can be written as y2 minus y1 over x2 minus x1. And in this case, it doesn't matter which point, either 0, 4 or CD that you use as point 1 and point 2. It just matters that you line up one of them first and one of them second. And that's going to get you the correct answer. So let's say CD is Y2. So, X2, Y2. Okay. And the point 0, 4 is, let's get this right, X1, Y1. Okay. That's really bugging me. I have that habit too of like sometimes just flipping my X's and Y's. But I always catch it. It's okay to have errors, but you just want to be aware of the errors that you make and know how to catch them and correct them. Okay. So anyway, if I have this as my x1, y1, and x2, y2, okay, and I use my formula, y2 is d. So I do d minus y1, which is 4. Okay, d minus 4 on the top. And then my x2 is c. C minus x1 is 0. Okay. This one. All right. So that's how you do that. That's how I would approach that one. I would absolutely approach it visually, armed with my algebra knowledge. And really, like those two together, if you can work visually along with your algebra knowledge, you are going places on the SAT, my friend. Oh, yes. Oh, look, this is my favorite number, 34. One of them. Okay, these ones. So common that I have you practice one a day. Okay. And they really love these where they say, okay, I've got a secret number that I can throw into this linear equation system and there's not going to be any solutions anymore. It's an odd thing to be really obsessed with, but I know that they've identified if you can solve this type of question, you are ready to work with a wide variety of systems of equations, and you can do so in a highly effective manner. You can really solve lots of stuff. So let's break it down. Take a look at it. Okay, so here. We want to know the value for k that will not have any solutions. So kx minus 3y equals 4, okay? And 4x minus 5y equals 7. Let me show you two approaches to this problem. If there's no solution to the system, that means one of the lines is like that and another one is like that, and they happen to be parallel lines. That's the only way that two lines will never touch, is that they must be parallel. Their slopes must be the same. If we wrote them y equals mx plus b, this is our first line. We'll call it y equals m1x plus b1. And the next line, y equals m2x plus b2. Then if they're parallel, m1 equals m2. That's for parallel lines. Okay, so what numbers are going to make the m's? These are in standard form, these lines. It's the ratio of this number to this number must be the same as the ratio of that number to that number. This is one way to do it. It's probably the fastest. It's definitely the faster way. And then I'll show you the slower way. So if I know that k to minus 3 is the same thing as 4 to minus 5, I just need to solve this for k. Multiply both sides by minus 3. Oh, and this is the way I write my ratios, by the way. I write them as fractions. I don't like that ratio notation. I very rarely use it, and I much prefer to think about these things this way. So k is equal to 4 times negative 3, which is negative 12, over negative 5, which is 12 over 5. 12 over 5. There it is. Bam. Okay. So it's really fast if you know this trick. And if you practice it every day, you'll remember this trick. This type of question is off on a lot of SATs. There's another way to approach it. So let's look at it. Okay. Remember when we had that system of equations up there? Oh, and I said there were 2 ways to solve for y once you get x, and I never showed you the second way, did I? Oh, well, there's lessons on it. We'll do it later. Okay, where I wanted to multiply by something so that I would eliminate one variable when I added them together, and I would get a 0, right? If your lines are parallel, if you do that to one variable, you also end up eliminating the other variable. It doesn't come down as well. Both of them eliminate. Why? Well, because the ratio between those two values is the same. So that's like saying, if I were to multiply this equation by 5, I got that number here. And if I were to multiply this one by negative 3, I got that number here. Okay. Then when I eliminate and add those together, I should get a 0. So let's figure out what k would do that. Okay. So then I will have 5kx. This is multiplying this 5 in here and here and here. Okay. 5kx minus 15y equals 20. Okay. And then negative 12x plus 15y equals negative 21. I don't care about these numbers down here. I'm just doing them because it's habit and it doesn't take very long. Okay, so I add these together. Negative 15y plus 15y is 0. 20 minus 21 is negative 1. And over here, I add these two together. So I have 5k minus 12. That's the coefficient of x plus 0. Okay, and I want 5k minus 12 to be 0. Why? Because I want to have eliminated x at that phase. So I say 5k minus 12 equals 0. Add 12 to both sides. 5k equals 12. K equals 12 over 5. Oh, we got it. It was up there all along. Well, we found it faster another way. But there's nothing wrong with doing both ways in your practice. And if you have extra time and you're not sure about a question, doing a question with a different algebraic pathway that you're confident in is a very solid error checking strategy. Okay, so now we go down to 10. Okay, this one's good. This is a nice parabola question. We have this parabola, y is equal to x minus 11 squared, and it intersects the line y equals 25 at 2 points. You want to see the long way or the short way first? I like showing the short way first. The answer is 10. It's very fast if you can do this visually. It's very fast. Okay. Oh, there it is. 10. Here's how. Okay. I know that this parabola, it looks like this. Here's the xy plane. Here's my x-axis, my y-axis. Okay. Here's the line y equals 25. Say it's up there. Y equals 25. And this parabola here has its vertex at positive 11 and goes up this way and up that way. All right. Now I could find where's that point and where's that point, and then find the distance between those 2 points. That's what we're looking for. This is like A and this is B, and I want to find this distance. How far is that? Right? Well, one thing I know, like I can take this 11, 0 parabola. Why not just shift it over here? Why not just like start it there? Because the whole structure, it's actually going to go up. I just want to get my graph like really pretty there. And then up here, I just basically moved A and B over, but they didn't change their relative position. the distance between them is going to be the same. And I know this visually. I can just move a parabola over. Okay. And so now I'm saying, now this new parabola, its vertex is not moved over 11. Its vertex is now at y is equal to x squared. Oh, sorry, no, that's its equation. And its vertex is now at 0, 0. Okay. Now y is equal to x squared. And so now I can briefly do a little bit of algebra. I can say, well, I'm going to say, but I know y is 25 at that point and that point, and I want to find the x values. There's a negative one and there's a positive one. So I go ahead and substitute that in for y. Y is equal to 25 is equal to x squared. And then, of course, I take the square root of both sides. But that's plus minus because negatives square to positive things too. So I have plus or minus 5 is equal to x. And if x is either plus 5 or minus 5, well, the difference between negative 5, 25, the distance between that, and 5, 25, well, it's just 10. It just moves 10. Okay. And let me show you this one in Desmos. So we're going to want to see up to 25. So I'm just going to change. We're going to make our Desmos a little prettier. And hey, I want 25 only. There. Okay. So let's put in the line y equals 25. And let's put in the equation y is equal to bracket x minus 11 end bracket squared. Like I promised you, this parabola is over there. And it had one point at 625 and one at 1625. Okay? So that's where it is. But then what happens if I move it? I'm going to show you moving it by just changing that to a d value. I'm going to do that there. And we had it out there at nearly 10, but it was at 11. If I move it back to where d is 0, then we're there. And our distance is still 10. And this is called the translation. And I know that the shape stays the same. And it allows me to get the answer extremely quickly. Like I didn't have that answer memorized. I did the question that fast because I can see these things on my mental whiteboard. And you will too if you practice with visualization every question. Now, is there a longer way to do this question? Absolutely. Here's how you could, if you had more time, check your answer if you weren't like super confident in your visualization, or how I can prove to you that that I'm right all kinds of different ways. So let's go ahead. We're going to recopy these equations. Okay, we're essentially doing linear quadratic systems where we have one function, y equals 25. That's a very simple linear function. And we have another function, y is equal to x minus 11 squared. Okay, if I set these equal to one another, like the y's equal to y's, then I would have 25 subbing in for y equals x minus 11 squared. Okay, and then I can do this a couple ways still. This is lots of ways. I would just take the square root right here. Plus or minus 5 is equal to x minus 11. Okay, and now we're going to get two equations. See how these two equations were much easier to work with? That's the benefit of translating it over, doing the algebra in your head like that, and knowing the answer. Okay. There's other ways to do it too visually. I've done this with step pattern in the past. I remember that was the first way I answered this question. Not as quickly as I just did. But anyway, so I'm going to have one question where I indeed have minus 5 over there is equal to x minus 11. We add 11 to both sides here. And we get 6 is equal to x. Okay, so that's the point 625. Okay, and then we get another equation from that when we have the positive 5. So that's 5 is equal to x minus 11. Add 11 to both sides. And that will give you 16 equals x. Okay, so that's the point 1625. And just to go back to Desmos so that we're really anchored here, that's like when D was 11, our 2 points were over there, and there was one of them right here and one of them right here, right? There's those 2 points, 625 and 1625. Distance of 10 between them because we were plus or minus 5. Why are we plus or minus 5? Let me just do like a x equals d, that line. I like it when these lines are dotty. I'm just a little bit fussy about visualizing that. So here you see, that's the midpoint, and it's symmetrical around that point by the plus or minus whatever. So since it was plus or minus 5, it's always distance 10 when I move this shape around. Do you believe me yet? I hope so. I hope you believe me. Okay, let's keep going. Back to the SAT. We're over halfway done, right? Yeah, that was halfway. Okay. All right, let's keep going. So here we are, question 11. This one is like properly tricky. Okay, so we know that over here we've got these 6 angles, and we know that if x plus y equals u plus w, which of the following must be true? Okay, so here are some things that we know. I know that these opposite angles here, x and t, are equal. Y and u are equal. Okay, so those are some things that I know just from like looking across this diagram. Okay, so in that case, we also are told that x plus y equals u plus w. But we already know that y equals u. Okay, so that's like saying x plus y equals y plus w. Oh, it really looks like I can subtract y from both sides. X equals w, therefore. So these two angles are the same. That means x equals t, w equals z. So here's some things we know. X equals t, w equals z. Sorry, I can just do this in a big line. Equals t equals x. Like all 4 of those angles are the same. Why? Well, anytime you have 2 lines crossing, if that's x and that's t, like they are in our diagram, then x equals t, because those are straight lines. I call this the kissing birds pattern because I don't want to forget it. And I just imagine 2 birds, okay? And this is how you draw 2 birds kissing. 2 circles and 2 crossing lines. You see how their beaks meet at the middle? And it's so cute. And you know, you won't forget that way. So by kissing birds pattern, these angles are the same. But since we were told this, but we already knew y equals u from kissing birds, then x equals w. So then we know x equals z as a result. X equals z. Yeah. Y equals w? Well, not necessarily. Y does not necessarily equal w. Y equals u, but not necessarily w. So we don't know that. But then z equals t? Yeah, sure thing it does. Look, all of those 3 are equal to each other, so z equals t. So this is probably tricky, but it's really fast, okay? So we know this is not true, and so it's 1 and 3 only. Done. I don't know what much else to say about that. You just want to be able to look at those types of diagrams and follow the logical conclusions as quickly as possible. If they give you extra information, that's going to be a key to unlock something about the question. All right, so we're back to quadratics, and we've already reviewed factored form, so we know that this will have zeros, okay? And we're going to exploit that fact, the same fact we've already talked about, to find where its vertex must be in terms of A, okay? And we'll verify it in Desmos because, hey, we're all about practicing with Desmos because it's going to build our visualization skills. We'll bring those skills to the SAT even if we can't bring Desmos. So let's go. Okay. So here, I know that this parabola has zeros, at 2, 0, and -4, 0. Okay, so I can sketch this parabola very quickly. Let's say it looks something like this. Oh, I couldn't get that straight. Why couldn't I get that straight? That's supposed to be my axis. And if A is positive, it's going to look something like that. All right, so that's going to be our quadratic with A being positive. And I know that the axis of symmetry is going to be right in between those 2 points, -4, 0, and 2, 0. Meaning, like, I know that the value of the vertex here is going to be CD. We're told that it's CD, okay? But I can find C. I can find this value just by finding the axis of symmetry. It's going to be directly in between the roots because quadratics are symmetrical. Since it's symmetrical, and we go directly between 2 and -4, well, that would be -1, wouldn't it? You can take the average of these two things. -4 plus 2 divided by 2 equals -1. Okay, so now, armed with that, we know this x value is -1. And the y, and that's going to give us the y value of the vertex. So let's go ahead and substitute that in. We were told y equals ax minus 2 times x plus 4. And now we let x equal -1. So we have y is equal to a times -1 minus 2 and -1 plus 4. Okay, and that's -3 times +3. So then we will have y is equal to a times -3. Oh, I'm doing everything, aren't I? Times 3. This is y is equal to -9a. Beautiful, eh? This is just easy. It's like easy when you can visualize and understand your quadratic anatomy. I will get you drilling questions about quadratics that are harder than anything you'll see on the SAT so that you crush these questions so quickly based on your thorough thrashing of quadratic vocabulary and quadratic anatomy. Oh, this one's a good one. Oh, this one's a good one. Let's put on our algebra shoes. Okay, I just promised you that I would give you hard questions, and then this one came up. All right, this one's properly hard. All right, we know that these two things are equal for all values of x that aren't this, where a is a constant. Okay, this looks very important, but it's only important to the people that make the question so that they know that they have a really sharp question with no loopholes. Okay, we don't need that. We don't need that restriction for our work. All right, so here's how we will solve this question. Okay, we are going to write out the whole expression. Okay, and we are going to say 24x squared plus 25x minus 47 is equal to -8x minus 3 minus 53 over ax minus 2. Okay. Oh, but this, sorry, ooh, my goodness, was also over ax minus 2. And that's a very strange way to write 2. And so we know that it's very inconvenient that they have put ax minus 2 in the denominator over there. So what we choose to do, we get out our inverse operations pen. You don't need a different color pen for this, but I like showing it this way, is we're going to bracket both sides of the expression. And we are going to multiply by ax minus 2 on both sides. Okay, and here's the cool thing. This will cancel this. But now this ax minus 2, it's like right over that other question. What am I doing? All right, it's going to multiply in and multiply that term and both of these terms. Okay, so to multiply that by both of those terms, let me just do that over here. Ax minus 2 multiplied by -8x minus 3. I'm just going to do that on the side so that I don't have to muck up my work under there. And then that will give me -8 ax squared minus 3ax plus 16x. So I'm going to write that as plus 16 minus 3a all multiplied by x. That's after I collect my like terms. And then negative 2 times negative 3, this is plus 6. Okay. All right. I hope that's okay. Okay. So now I'm ready to go down to the next line. Wow, wasn't that convenient? It knocked it off the denominator in that one. So there I have just 24x squared plus 25x minus 47 is equal to this stuff, negative 8ax squared plus 16 minus 3a, put it in brackets, x, plus 6. Oh, and then this will cancel that on the bottom, minus 53. Okay. Plus 6 minus 53, whoop-de-doo, that is minus 47. Okay, that was the only real simplification that I need to do there. And so now I have this, I don't need to write it out again, but I'm going to write it out again. Okay, whatever. Is equal to all this stuff. Okay, I'm not going to write it again. But what I know is that this term is my x squared term, must be equal to that one. This 25x must be equal to that a 1. Okay, so here I got two different equations. We'll find that actually they're both really easy to solve. If I have 24x squared equaling negative 8ax squared, I know these two must be the same. These two terms have to be the same because x squared is x squared. So the coefficients must be the same on both sides. We already have 47 equaling 47, but negative, both of them negative, okay? And so I have this one to solve. So now I can divide both sides by, let's say, negative 8x squared, and divide that by negative 8x squared. Cancels, 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 cancels. I was just trying to isolate a, so I divide by that. That gives me a, and this here is cancels, cancels. Those go away. 24 divided by negative 8, negative 3. Okay, so there it is. That's the answer. But, oh, and in this one, yeah, they're just asking for a. They didn't say, like, what's a minus 1? And then you're like, oh, no, I made a mistake. They wouldn't do you that dirty with this type of question. This type of question is, this is a 790 question, like a knock you down from 800 question. Probably the hardest question on the whole SAT math-wise. Okay, and now let's check this term over here. If we know that it's equal to 25x, so we'd have this little mini equation. 25x is equal to 16 minus 3ax. Divide both sides by x, and you get 25 equals 16 minus 3a. Well, if I subtract 16 from both sides, I will get 9 is equal to negative 3a. Divide both sides by negative 3. Negative 3 is equal to a. Same. That's just a way of checking your answer. So that is to say that all the way up there, these two expressions are equivalent, or they're true, for that value of a, negative 3. But of course, x cannot be 2 over a, because that would mean this is a 0 in the denominator. And the question creator just didn't want you to have to think that there was the tiniest of exceptions to their statement here, that it was true. Okay? Because I don't know, was it essentially, it was undefined for all values of a. Anyway, whatever. Okay, next question. Question 14. This one's very simple. We look at these and see solutions to some quadratic formula. Like if you've done enough work with quadratics, and you're going to get doing one of these a day, you will see that these all were outputs from the quadratic formula. So let's feed that to the quadratic formula. Do you want to feed it the fast way or the slow way? Fast way, please. Good thinking. Here's the thing I can do. I can divide that side by 3 and this side by 3. I get x squared plus 4x plus 2 equals 0. All right. This is not necessarily like the same equation as that, but it has the same zeros. I just realized I promised you I was going to show you Desmos for a previous question, and I never got to it, did I? I'll go back in just a second and take a look. Maybe I did. I hope I did. No, I didn't. I remember which one it was. The one with zeros, and we had to find the vertex. I'll show you. Okay, so these two equations are not necessarily the same. This one is stretched by factor 3. It's 3 times stretched away from the x-axis. However, it will cross the x-axis at exactly the same place as this equation, which is great news for us because we just want to know when the whole thing's equal to 0, like when y equals 0, which is only going to be 2 values of x. So I make a little mini chart here. Doesn't matter. Doesn't matter how simple. B equals 4 and C equals 2. All right, I do these in my head because I do a lot of quadratic formulas. So I do it in my head. I have a really clean quadratic formula algorithm going in my head. But anyway, quadratic formula would be x equals negative b plus or minus the square root of b squared minus 4ac over 2a. And you memorize the song so that you memorize the quadratic formula. And then we're just going to input in. So x equals negative 4. So that's inputting b for 4, plus or minus the square root of 4 squared minus 4 times 1, which you could or could not write, doesn't matter, times 2, all divided by 2 times a, which is 2. Okay, and then we get x is equal to, and we can already see we got negative 4 divided by negative 2 as our integer part. So we can eliminate these two. Okay, it's going to be either that one or that one. And you know what? We can eliminate that because how are you going to get a 3 in the denominator? I mean, seriously. This is going to be this root 2 thing here. But let's see why. Okay, let's prove it to ourselves. Let's prove it to ourselves. So negative 4 plus or minus 4 squared is 16 minus 4 times 1 times 2. 4 times 1 times 2 happens to be 8. 16 minus 8 happens to be 8. So that gives us negative 4 over that was 2. And I don't know why they gave us this one. I mean, why didn't they give us root 4? Negative 2 plus or minus root 4. That would have been a better catch more people bad answer than that. Okay. It's this. Why is it that? Okay. So here's how we would simplify this output. I like to split these up around the plus or minus, and most people will. Okay. So this is x is equal to minus 4 over 2, which is just negative 2, plus or minus the square root of 8. 8 can be written as 4 times 2, I think you'll agree, divided by 2. Okay. And then we simplify. X is equal to negative 2. That's for negative 4 over 2, plus or minus. The square root of 4 is just 2, I think you'll agree, multiplied by root 2. That's this root 2 still in there, all divided by 2. Oh, but that would just cancel. So x is equal to negative 2 plus or minus root 2. Done. So that's that one. Okay. And then it's, this one here. Bloop. Cool. 14, 15. Okay. Helps to not write all over your questions. I mean, they do want you to do all this rough work on the page, but you can be a little more judicious in your use of space than I am being. Okay, we are given a linear equation here. Cool. All right. And we want to know, and it converts Celsius to Fahrenheit. And so this type of question, it can help to have your general scientific knowledge there so that you've like done some work in Celsius and you know that like 0 is the melting point of water and 100 is the boiling point of water. And they're not two like totally arbitrary numbers like, what is it, 32 and 212 or something? Did I just embarrass myself? Is it not 212, the boiling point of water? I don't know my Fahrenheit that high. What are you kidding? Like, I know that I bake salmon at 420, and that's certainly not 420 Celsius because my oven was made in the United States. But otherwise, I'm Canadian. I work in Celsius for the most part. Anyway, let's keep going. But it does help to know those things, and that 1 Celsius degree is bigger than a Fahrenheit degree. Like a Fahrenheit degree is much smaller than a Celsius degree. So if we increase temperature by 1 degree Fahrenheit, that would give you this much increase in a degree Celsius? Yeah, Because imagine if you do like f plus 1, that plus 1 is going to be multiplied by this. So it's going to be raising the output of this whole formula by 5 over 9. So 1 is correct. Let's check this one. 1 degree Celsius increase is equivalent to a temperature increase of 1.8 degrees Fahrenheit. Well, that's also true because you can take this fraction, and if you want to know what's it like going the opposite direction, you'd flip it. Okay. And we could actually rearrange this equation. Okay. C is equal to, you don't have to, but you could. I just look at it and I'm like, yeah, I know that makes total algebraic sense. But if it doesn't make algebraic sense to you yet, just rearrange it because we practice rearranging formulas like this. Here, my bold inverse operation that I'm going to do is going to be multiply by the reciprocal. If I multiply this side by 9 over 5, I got to multiply that side by 9 over 5. But then that 5 cancels that 5, that 9 cancels that 9. That's why I multiply by the reciprocal. It's a one move a fraction across the equal sign. So there I got 9 over 5c is equal to f minus 32. Okay, that's a new formula that I might use, or I might do 9 over 5c plus 32 is equal to Fahrenheit. Now I can see if I increase this by 1, this is going to change by 9 over 5. So this is also true. But then a temperature increase of less than a degree Fahrenheit is going to result in an increase of 1 degree Celsius. You're just like awareness of a Celsius degree is bigger than a Fahrenheit degree should just immediately throw that out. I'm not going to show you the algebra that that's not true. It's just not true. You just look at it and you just know it's not true. So it's 1 and 2 only. Also note that this is the only one that accepted both of the things that we both found were true already. So since these both are true, they can't be those because it's not only. Okay, it has to be that one. Yay, let's keep going. All right, finally we're at the code in your answers one. So it helps to review this, and you can't look at this often enough. Writing in fractions is great. Code in your fraction bar, and then you'd put like your numerator, code the fraction bar up there, denominators down here, right? Easy. If you want, you can code decimals too. Decimals are fine to code. Just be careful that if you have repeating decimals, you need to fill the whole chart. You cannot do 0.6. You cannot do 0.66. You cannot do 0.7 or 0.67. You need to either fill it and don't round or fill it and round. And you don't need to code a leading zero. Okay, do not code a leading zero. Okay, these are the acceptable ways. I would code it this way because I might make a mistake and code 0.66. They might not like that. That might mean the difference of me getting into Harvard or not. Can you imagine? That's your life story? Yuck. Anyhow. Okay, here we go. If x is greater than 0, what is one possible solution to this equation? Well, let's find it. Well, if x were 0, that would be a solution, right? Because we would have 0 there and 0 there, and 0 equals 0. So that's too easy. So they don't want you to just write x is 0. Okay. Also, your answers will always be positive numbers of some kind, positive rational numbers. So let's go. So here's how we will work on this. We would get out. I would copy it out. I mean, you can work on it this way. That's fine. You can do that. I don't hate it. I don't love it either. Okay. So anyway, I would write it out again. X to the 3 times x squared minus 5 equals minus 4x. I mean, if you can write it there and then write the result, what I'm going to get in my next line, which is going to be x squared times x squared minus 5 equals minus 4. Okay. And now we're going to go ahead and I'll just multiply that x squared in. You got x to the 4 minus 5x squared. This is distributing these in. And then we're going to also add 4 to both sides because we want to set these equal to 0. Plus 4 is equal to 0. Now we have a quartic, which is really like beyond the limits of what we usually see on the SAT. Usually working, if you're doing algebra, you're usually working on quadratics or easier linear stuff. But here we go to quartic. It's x to the 4, but it's what we call quadratic and x squared. Like I can still factor this into finding my two numbers that add to -5 and multiply to 4. And those numbers are -4 and -1. Okay, equals 0. Okay, and now here we go. We're told x is greater than 0. That's going to come in just a second. All right, see? So what did you do? Okay, look. This is x squared squared. This is x squared. All right? So it's what we call quadratic in x squared, where I can still factor it, and then x squared ends up here. All right? You'll notice if I expand this, I'll still get I can go back this way. And I'm just sort of like, in a quick way, how do I get you to spot this in the future? You see a trinomial, you know that factoring things like x squared minus 5x plus 4 equals 0 is a thing we do, right? This factors into x minus 4 times x minus 1. But if these are like to the 4 and to the 2, well, that's still a trinomial that's quadratic in x squared. It's not quadratic in x, it's quadratic in x squared. And now there's one more thing that we can do. I've scrawled all over this, but I'm going to bring this up here. X squared minus 4 multiplied by x squared minus 1 equals 0. Both of these are differences of squares. So when you have a squared minus b squared, that's always equal to a plus b multiplied by a minus b. Always. That's an identity that we can memorize, but we also want to know why, and I'll teach you in the quadratic section. You should have learned that from me in the quadratic section, if not from your algebra teachers. So here, x plus 2 times x minus 2 is x squared minus 4 times x plus 1 times x minus 1 is x squared minus 1 is equal to 0. And now we're looking for positive solutions to this. And that will give us 1, and that would give us 1. So x is either equal to 1 or 2. Both acceptable answers. Isn't that a great question? It's so great. Where it's really tricky. It's got some real stuff that can like stump a lot of students. And the answer is 1 or 2. It's fun. It's fun that way. So how else could we approach that? Gosh, wouldn't it just be great? Okay, if you were the type of student that looked at that, got confused, and said, I don't know, but x is bigger than 0. Let's try 1. Let's just try. Okay? Don't skip and leave and don't put something in. Skip and leave and come back later and try if you're stumped. So just say, okay, x is 1. 1 is the easiest thing to try. Watch this. Okay, I'm going to do this in red over here. Okay, just up a little bit. Yeah, right there. X cubed times x squared minus 5 equals -4 times x. Let's say, I don't know, x equals 1. We'll try. I'm not trying to say like, oh, I'm some dumb person that's just going to try x. I'm saying I am being brilliant by being like, don't know, I'm going to go forward though. Go forward. Okay, when you don't know. So then we're going to just try 1. So 1 cubed is 1. 1 squared is 1 minus 5 equals -4 times 1. Okay, 1 times, well, this is -4, isn't it? -4 is indeed equal to -4. So x is 1 is a solution. Cool, eh? Cool. I think it's cool. You may not think it's cool, but then again, you and I would then disagree about a lot of things. Oh, fractions. That's not scary at all. Never be scared of fractions. Fractions are your friends. So let's do this one. If 7/9 x minus 4/9 x equals a quarter plus 5/12, what's the value of x? You know what? I can't see any shortcuts here besides just doing it. So I am going to scale up that 1/4 to 3/12, because multiplied on bottom by 3, plus 5/12 is equal to 8/12. Oh, that's equal to 2/3. Whatever. We'll do that later. Do that. I got more lines coming. 7/9 x minus 4/9 x. Well, that's just 7 minus 4/9. So that's 3/9 x is equal to this. All right. 3/9 is so that's 8/12. And 3/9 I'm just going to write as 1/3. Okay. 8/12 I can honestly say is 2/3. So 1/3 x equals 2/3. I mean, come on, x is 2. I can multiply here both sides by 3. That will cancel that. And multiply over here by 3. That will cancel that. X equals 2. And then you can go ahead. You could substitute that in if you have oodles of time and you want to test it. 7/9 times 2 is 14/9 minus 8/9. 14/9 minus 8/9 gives you 6/9. 6/9 is 2/3. We also already showed that 1/4 plus 5/12 is 2/3. So x is 2 works. It's amazing. Okay, check your answers. Good for your understanding, and it's good for your score. Okay, here, weird looking diagram. Figure not drawn to scale. Okay, sure, fine. 2 isosceles triangles are shown above. Okay, they're isosceles, and that's what these marks are telling me. That's an isosceles triangle. That's an isosceles triangle. All right. If we have this relationship between z and y, and we know y, wow. Okay, so we know a lot here. So we want to know what this value of x is. So I'm going to just zoom out here for a second. I'm going to write down my funky equations. Y is equal to 75. I'm just going to put that in. And then 180 minus z equals 2 times 75. My goodness, there. Now I can zoom back in and just see all that stuff at the same time. So I will have this is equal to 150. So I want to subtract 150 from both sides. So I'll have 180 minus 150 minus z. It's actually kind of awkward. I'm also going to add z to both sides. Ugh. Just to move it over there and make it positive. So on this side of the equation, I've got 0 plus z, so just z. And then over there, I've got 30. Okay, I've got the value of z. It's 30 degrees. If that's 30 degrees, okay, it's no longer z. I now know it's 30 degrees. I know that one's 75 degrees. Okay, so now, what's this angle here? Well, it's an isosceles triangle, so it's going to be the same angle as that one. So it's actually going to be, wasn't that fun? 75. So there was a shortcut that I didn't take. This was a kind of expression that was telling me, ha ha ha, you got your 180 minus z is going to be 2 times y. Well, that means actually y can go in here and here. Wow, that was kind of fun that they did that. Gave us that opportunity to save some time. And it doesn't save you that much time. And like, even if I used something like that, I would still be like, I'm gonna go back and check. I'm like, don't want to be fooled. Anyway, so now I know that that angle is 75. So what I know here is that that angle is 180. So 180 equals 75 plus x. So subtract 75 from both sides. 105 equals x. Yeah, that's that angle. That's how I would do it. Okay. Kind of crazy. At a lunch stand. All right, cool. Each hamburger has 50 more calories than each order of fries. Set up an equation right away. Okay, you see that? 50 more calories than each order of fries. So I'm going to say H, that's a hamburger. You're not going to write this out, but you're going to remember H is hamburger. F is fries. It's not just fries, it's the calories. And this is hamburger calories. It's not numbers of hamburgers, it's calories from a hamburger. Okay, so now what we know from this is that H equals F plus 50. Okay, the hamburgers have 50 more calories than an order of fries. And that's given by this word equation. Sorry, the word equation up there gives me this algebraic equation. And then I know that 2 hamburgers and 3 orders of fries equals 170 calories. Sorry, 1700 calories. Okay. Well, I could set this up for an elimination strategy, but I'd much rather just substitute in fries plus 50 there for H. So this is the value of H, and I'm going to substitute that here. So I'm going to have 2 multiplied by fries plus 50. That's 1 hamburger is fries plus 50 plus 3 fries equals 1700. Okay, this is going to give me 5 fries total, 2 fries plus 3 fries, and then 100. So I'm going to minus 100 from both sides. And then I will get 2 fries plus 3 fries. This was canceling out. 50 times 2 is 100, so that's just 0. Skipped a step there. I hope you don't mind. I skip a step. Is equal to 1600. Well, let's divide this by 5. Because that's 5 fries. I'm skipping another step. I skip a lot of steps. My goodness. Fries are equal to, that's what, 4, no, 3. Why is this so hard for me? It'd be multiplied 320. That was weird. That took so long. Okay, 320 is an order of fries. Cool, eh? Okay, so that's how you do that one. Last one. Triangle one. Okay. In triangle ABC. Oh, what do you mean, triangle ABC? You didn't give me a diagram. Of course they didn't give you a diagram. Draw one. Pshon, pshon, pshon. Draw your favorite right angle triangle. The measure of B is 90 degrees. There it is, B. ABC. So BC is 16 and AC is 20. 20 here. Okay, and BC is 16. That's actually the longer side. This side is 12. How did he do that? How did I know? Well, I did this very quickly in my head. No, I didn't. 20 squared equals 16 squared plus x squared. And then I solved it in my head in a flash. No, I did not. Okay, I recognized that there is a much easier to work with similar triangle that has side lengths 5, 4, and 3. Notice that these are in a ratio of 5 to 4. And so the other one will be the smallest one. They're in a ratio of 5 to 4, but they're scaled up by 4. So I scale up the 3 side by 4. Okay. And the 3, 4, 5 triangle is absolutely one that you want to memorize. You want to memorize this triangle and very quick, just know that it would map to bigger and smaller sizes. This will also be true, like if I do here, he's getting out a calculator on the non-calculator section. How dare he? Yes, I know. 220 square. I'm just doing it to show you. I don't need to do it to solve the question. Okay, so the square of 20 is 400. Well, what's the square of 16? 16 squared is that. Okay, plus 12 squared. 12 squared is that equals, oh, wow, it works. He was right. It is 12 over there. Okay, why do I have a 2? Anyway, that's an arrow. Anyway, all that is to say is that I want to get a really good diagram with all my sides labeled and my corners labeled. So BC is 16. So that means C is over there and AC was 20. Okay, and AB is 12. But we're not told AB is 12. We use Pythagorean theorem to find that. Or just scale up your triangles. Okay, and this is non-calculator section. If you didn't know that 12 squared was 144, you might be like, I have to take the square root of 144. What's going on here? Anyway, okay. Triangle DEF is similar, okay, to triangle ABC. So I'm going to draw DEF. Here's DEF. Okay. where every side is 1/3 the length. This is dumb. I'll show you why it's dumb. It's dumb because they're trying to waste your time. They're not dumb. Their question is dumb because, and I'm going to write that as 12/3, even though it hurts me, I'd rather write 4. Okay, so those are the side lengths because we're told that every side length is 1/3 the side length of the corresponding side in the other triangle. Okay, and we want to know the value of sine f. Okay, so here is the one we want, sine f. And we have a beautifully labeled diagram. And sine is opposite over hypotenuse. So 12/3 over 20/3. And then we recognize that this is divide two fractions, so we flip and multiply. Oh, come on, don't flip. I'm doing this the long way right now. There is a very fast way that I do without drawing a diagram. I just have the triangles in my head. It's very clear. I'll show you in a second. So I flip and multiply. 12/3, keep the top, flip the bottom and multiply. 3/20. Okay, pion, pion. This is like a 3. That's like a 5. 3/5. I could code that as a decimal as 0.6, or well, you would just code 0.6. That's fine. Okay. Aren't those numbers familiar? Yeah. They come from the 3, 4, 5 triangle, and the similar corner that we're looking at there would correspond to corner F. It's just the ratio of sides are a little different, but the ratio between sides is the same. Doesn't matter how I scale it up or down. So it's opposite over adjacent. That's how I get this one. They like these types of questions that see, maybe you don't know your Pythagorean triples, like the 3, 4, 5 triangle. This is a Pythagorean triple. Other ones include, a very quick lesson on them, the 5, 12, 13. You will often see, it's like, this is the by far most common. This is the not close second, but still beats the other ones. You could occasionally see this one, the 8, 15, 17 triangle. And you might also see some other fun ones like the 25. That's weird. 24. I was already writing 24 up there. 7 triangle. Or there's also like the 41, 49, and there's 11. This one is a cool 61, 60. Okay, triangles. You might see, but probably not. Okay, is probably going to be this one or this one. And so then one of the activities that you will be doing is scaling these up in our daily algebra practice, like making a little chart like 3, 4, 5, and then saying that could be a 6, 8, 10, or that could be a 9, 12, 15, and blah, blah, and just listing a whole bunch of Pythagorean triples so that you recognize them instantly. Like I, from those two numbers, recognized a Pythagorean triple, knew instantly it was that one with no calculation necessary, just pure memorization. And it's just the next one on the list, man. It's just 12, 16, 20. It's just, I know that. I recognize those ratios any day of the week. I dream those ratios. So anyway, those are some strategies for, I hope I wasn't too sarcastic when I showed you the long ways to answer these questions. If you get any of these questions right the long way, you still deserve a pat on the back. If you get them right the fast way, that's fantastic. And if you got them wrong, but you learned something from this, that's the best, actually. Give yourself a pat on the back. So thank you for showing up for your learning. I appreciate you. This is Grant the SAT Genie saying bye for now. And remember to check your stuff in Desmos. Bonus, let's look in Desmos at that one thing. Okay, I forgot I haven't shown you yet. Okay, so we were given this parabola A bracket x minus 2 times x plus 4. Okay, this was the parabola we were given. It exists over here. Remember I told you that its vertex would be somewhere around like x equals negative 1. So I'm going to put that in, x equals negative 1. I'm going to make that a dotty line because I like my axis of symmetry to be a dotty line. It's not really like a function. It's just a place where good stuff happens. And then notice that as a changes, so does the value of the vertex. See? But the x value is always there. So I told you I would prove it to you, and now I have. So if a is -1, it's up there at 9. If a is 1, it's going to be down there at -9. And you'll remember that that we said that it was -9a was the value of the vertex. And indeed it is. Hooray. So that's it for me today. Thanks very much for showing up for your learning. And if you've made it this far, the secret code word is going to be impermanence. Email me with impermanence in the subject line, and I will send you a virtual high five. Bye for now, everybody.